Okay, I want to go over some of the AP table examples, which are, this is from 2012, we have one from 2013 and 2014. Then I gave you some practice. So maybe going through a couple of them with you. Again, the more you practice, the more the better you're going to get. So let me go through, let's go through two of these examples, and then you can try the other one on your own. You feel free to, obviously if I go too fast, just pause the video and copy down what you need to copy down. So we've dealt with tables in the past, and all of these questions are from an AP exam. So it combines stuff that you've learned from units 1 through unit 6. And it also includes the average value, which is just taking, it's just another way of saying average value is average amount. Since we've been dealing with average amount or a total or accumulation, we know how to find an amount. And today I will add in how to find the average amount. And it's just as simple as dividing by the interval. And then obviously velocity and acceleration, position, velocity, acceleration if you're taking derivatives, and acceleration, velocity, position if you're taking integrals. Okay, so let's look at this first example here, which we've seen something like this before. It says this is W of t. This is not the derivative. This is W of t, and t is in minutes. Estimate the derivative of 12. Well, here's 9 and here's 15. So the first derivative, to estimate the first derivative, we're going to use the slope of the secant line given a table. So it's just change in y's over change in x's. Okay, and this is a calculator problem. Okay, and then if you round to the nearest, if you go to 3 decimal places and round, it would be a 7. If you truncate your answer, this would be a 6. Both are acceptable. So what does that mean? What does the first derivative at 12 represent in the context of this problem? Well, if your first derivative is positive, that means what? That means the temperature is increasing, not the rate increasing, but the water temperature is increasing at a rate of 1.017 degrees Fahrenheit per minute at t equals 12 minutes. Okay? So we've done that. Okay. Now, this one, we're going to integrate W prime. When you integrate W prime, you get change in W. And this comes from the second part of the fundamental theorem of calculus, which we haven't done a whole bunch of, but we've discussed it. If you integrate W prime, you get change in W. And we'll spend more time on this later on. But this comes from the second part of the fundamental theorem of calculus, and it's also a different form of the net change theorem that we've discussed. Okay, so that one is something new. Okay, so you can use your calculator, and what you need to realize is the units are very important here. When you integrate degrees per minute, you get degrees. Okay, so this 16 is 16 degrees Fahrenheit. The water has warmed by 16 degrees, or the temperature, however you want to say it, the temperature has increased by 16 degrees. That's what this represents, the change in temperature. or it could be the change in position if you were integrating velocity. Okay? Now, it's the change over this time interval. So again, make sure to include your units and your time. Noun, units, time. Okay? Again, pause if you need to. Part C. It says find the average temperature. Now, we know how to do this 0 to 20 of WT using a left Riemann sum. Okay, so this is the table for WT using a left Riemann sum. Left height, left height, left height, left height. You're going to have 4 rectangles you're going to use. It has a change in X of 4, 5, and 6. So the widths of your rectangle are all different. So this is what you get. 4 times the left height of 55 plus 5 times the left height of 57.1 plus 6 times the left height of 61.8 plus 5 times the left height of 67.9. So we've done that. That is the antiderivative of WT. Now, when you divide it by the interval of 20, that is an average amount. And let me show you how that works. So if we integrate W, and I've talked about this before, if you integrate degrees, you get degrees times minutes. If you integrate a W prime is degrees per minute. So if you integrate degrees per minute, you get degrees per minute times minutes. Okay, but on this one, we're integrating W. So you're integrating degrees. When you integrate degrees, you get degrees times minutes. So all of this, the unit for all of this, for this left Riemann sum, the unit is degrees times minutes. But they're asking you to define the average temperature. So if I divide it by the time that has passed, which is 20 minutes from 0 to 20, I'm going to have degrees times minutes divided by minutes. And that's going to give me my average temperature. So that's what I wrote here, okay? This average amount, you're going to integrate an amount, you're going to integrate degrees, and you get degrees times time. You're going to divide it by time, and you're going to end up with a unit of degrees. And that is the average temperature. Okay? That is the average temperature over the interval from 0 to 20. Don't forget your time, which I did, and I squeezed it in there. So 60.79 degrees Fahrenheit, because we're using a left Riemann sum, and if you look at the table, the values are increasing. So we have an increasing function. Okay, strictly increasing means it's increasing from beginning to end. And we're using a left Riemann sum. So you need to know that when the function is increasing and you're using a left Riemann sum, that you have an underestimate. That was one of the first things we learned in the unit. So make sure that you know that. Okay. question D. It says this is the model from 20 to 25. This is the first derivative from 20 to 25. Based on the model, what is the temperature of the water at T equals 25? Well, they're giving us a T value, and they're asking us to find the Y value. And we did that in our little practice handout today. I gave you T values or X values, and you gave me Y values. By integrating, by taking the integral of the derivative, that's going to give you the Y value. But be careful, because this is the model from 20 to 25. So this is only going to give you the change in temperature, or the temperature from 20 to 25. So if you look at your table, what was the temperature at 20 minutes? Don't forget your initial condition. And this is where that net change theorem comes into play that we talked about yesterday. The net change theorem here. Your initial condition, you have to use your initial amount at 20 minutes. And then when you integrate 20 to 25, that will give you your amount from 20 to 25. So that one's kind of a tricky one. And again, this is something we discussed with the net change theorem. So again, you can use this notation. You do not have to write all of this out. It's a lot less writing if you just write the correct notation, but you must write all of this before using your calculator. Okay, so that's example number 1. Okay. Then we have example number 2, which I am going to let you do example number 2 because it's very similar, and I'm going to do example number 3 because it's a little bit harder. Let's go to example number 3. Oops. Okay. So example number 3 here comes from 2014, and it's a non-calculator one. We have V of A, or V sub A, I should say. And V sub A is given in the table, and it's meters per minute. So this is the velocity. So this is a different table because they're giving us technically the first derivative in the table. Okay. Find the average acceleration. Well, that's the same as the last one. They gave us, in the last example, they gave us position and asked us to find average velocity, in a sense. In this one, they're giving us velocity and asking us to find average acceleration. So you should be able to do that. You can stop the video and try it on your own. Now, from 2 to 8. Okay? All right, let's check your answer. Hopefully you stopped the video. If not, do that now and try it. The average velocity, the average rate of change, the average acceleration is the average rate of change of velocity. And again, meters per minute, if you take the average rate of change of meters per minute, you get meters per minute squared. Or you could say meters per minute per minute. Okay. Do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t between 5 and 8? What does that sound like? At some time between 5 and 8, the train's velocity is a negative 100 meters per minute. Well, that sounds to me like we're talking about the intermediate value theorem. Remember that? So what does the intermediate value theorem state? Intermediate value theorem states that there must be a time between 5 and 8 where the such that the velocity is negative 100. Why is that? Well, because at 8 it was a negative 120, and at 5 minutes it was 40. So if it was 120 here and it was 5 here, sometime between 5 and 8 it had to be a negative 100. In order to use the intermediate value theorem, you need to make sure that the function is continuous. That was one of the conditions of IVT. Now, does it say that V of A is continuous in the given information? No, it does not. So it says V sub A is differentiable, therefore it is continuous. So that's where you get the continuity part from. So this is the condition that needs to be met for IVT. Okay? Going way back on that one. All right, then you have a trapezoidal sum with 3 sub-intervals. So you should be able to do that one. So pause the video and see if you can do a trapezoidal sum with 3 sub-intervals. Okay, so I would assume that you would have gotten this. 1/2 the base. You have same base on this one. I'm sorry, the height. 1/2 the height. You have 3 trapezoids, you have 3 heights. Okay? And then the sum of the 2 bases. Okay? So this is the trapezoidal sum. And maybe you put that as your answer only, but there's a reason, again, why they said at t equals 2, the train's position is 300. Again, you need to recognize that that is your initial condition. If you're starting at 2 and going to 12, and they want the expression, what does it say here? Write an expression involving the integral in meters at t times t. Use the trapezoidal sum with 3 subintervals to approximate the position. So if you don't use your initial condition, you're going to be 300 meters off. Okay? So again, now you know to look for that, because that's the second time we had a problem where we had to use our initial condition, and we're using, again, the net change theorem. So now you know to look for it. Okay? So by taking your negative 450 with your initial 300, what does a negative 150 mean? Well, that means that you're 150 meters to the west of the origin, or to the left. Now it says moving east. It was moving east, so that's why I used west. If it's moving east, then negative means it's to the west. And again, the position of the train, 150 meters, and then the time. Noun, units, and time. Okay, and then let's take a look at the last one, which again is probably not one of your favorites. You've got a second train traveling north. So you have one traveling east and you have one traveling north. North and east are perpendicular. So therefore we have a right triangle. Find the rate in meters per minute at which the distance between train A and train B is changing at time t equals 2. Do you know what that sounds like? Find the rate at which the distance between the trains is changing. That is your special related rate questions. Related rate questions. So we have train B that's going north, we have train A that's going to the east, and then we have the distance between them. So if you want to pause the video and practice your related rates, you can do that now. Okay, hopefully you paused and tried it on your own, and this is the answer you should have come up with, 160 meters per minute. So if you didn't get that, go ahead and pause the video and you can copy this down. We took the a squared plus b squared equals d squared, and we took the derivative with respect to time, if you remember doing all of that. Okay, derivative with respect to time. I divided everything by 2 because I can, and then I used all the given information, find the unknowns, and plugged in my rates and all of that good stuff. So there's a nice related rate question. Okay, so as you can see, you have to remember everything from units 1 through 5, because you never know what they're going to ask. So you can go ahead. I'm going to put up the solution to example number 2 right now. So when you try it, you can come back and you can check your answers. But go ahead, make sure you try it and then come back and come back to the video and pause it. Check your answer. And then pause that, check your answer. Hopefully you've tried it before you're checking your answer. And then here is the end. So that's example number 2. So this one has mean value theorem in it, average again. So yeah, again, don't get discouraged, keep practicing. I gave you 4 more tables to practice, and just keep plugging away at them, and the more you do, the better you'll get. And if you want to print them out again and do them from beginning to end, there's nothing wrong with redoing the free response questions that you've already done. Just keep practicing.